Okay. So suppose you have taken a system of certain size and you have this hard spheres or discs sitting randomly at various places. Now, if it is, and let us say we are talking of a fluid phase, so that any sort of positional correlation is short range. So then, if I take this point or this disk, for example, there are other disks around it whose positions are correlated to its position up to some distance. So if you remember the plots for g of r, the KR correlation function is a function of r. For hard spheres, it goes something like this, and then it basically becomes one. So over some short distances around this, there are positional correlations. Beyond that, it is lost. So then, if I am now, when you numerically do it, if you remember, so you have to take one of these objects as your origin, and then look where are the other ones relative to this, and that way you have to sort of calculate g of r. Now, when you're doing numerics, getting more data means your statistics improves. Okay, so if you have a system which is finite without periodic boundary condition, only some atoms or some of these disks close to the center of this whole region are the ones which you can use to be at the center. Because if you choose one of these sitting here to be your center, you are not sort of capturing the correlations that you want to capture here, because this is at the boundary, so it doesn't even have anything here. So you cannot take this to be at your center. You're following my point, Kaustav?
Yeah, my question was more on the lines of, let's say I take a center, like the center of the square as my initial point, and then I'm sort of calculating g of r. So if I, let's say, calculate at r equals L, then in the direction, in the like horizontal plane and the vertical plane, I'll definitely find a particle if I impose periodic boundary conditions.
Yeah, but you don't count particles that are at distance L.
Yeah, so r will vary from 0 to some L by root 2, I guess, because that is the maximum distance we need to worry about.
No, not really. So basically you have to, so you choose this as your center, okay? And you ask, so if you take a sort of slice, you ask how many particles there are in this annular region at some distance r from it within a narrow this thing which is dr. Now, when you are measuring such distances, you have to consider what really is. So, suppose you have applied periodic boundary condition, and you have one which is here, and there is another one which is, let us say, sitting here.
Sorry, sir, but your screen share stopped, I think.
Okay, so suppose there is one here, the other one is sitting here. Within your box, this distance is something, or to be extreme, let us say this is at the right at the boundary. Okay, so if this distance is some x1, let us say, within the box, the distance between this and this would be L by 2, x1 plus L by 2. But when you apply periodic boundary condition, the distance between these two would really be L minus x1, because this one also is repeated here. So this much is L minus x1. Is that what you are asking?
Yeah, but in that strip, we are counting the number of particles. But what are we varying R from? Like 0 to L by root 2, right? I mean, I would think so.
So the maximum distance you can have is
Yeah, from to the corner. Yeah.
Yeah.
So when I draw a circular strip around it, like some part of the strip would be outside the box, in the other box, like if it's periodic. Hello.
Yeah, I can hear you.
Yeah. So yeah. So some part of the strip at R equals some value greater than L by 2 and less than L by root 2. Some part of the strip will be outside the box.
Let us say.
Yeah. So in the neighboring boxes, I'll have to take account of the periodic boundary conditions in the sense that particles sitting in that strip would be coming from this box only because they are perfectly correlated if they are in a periodic condition.
Yeah. So when you take any of the particles at the center, you fix, and suppose you are calculating how many other particles are there at a distance r, you consider all the particles and see which ones are at a distance r, or let's say r means r between r and r plus dr, after taking into account the periodic boundary condition. That's what you have to do.
Yeah, okay.
Sir?
Yes.
Sir, I have a question regarding the method you asked us to impose the periodic boundary condition. Say
Right.
two particles are at x1 and x2. Okay. You ask to, I mean, say that the minimum distance is L minus mod of x1 minus x2. So say I have a box, I mean the origin is 0. I have two particles placed at x equal to, say x equal to something r or r and r, both at r. Okay. And say y is also there. I mean 2 points sitting at the same point, two particles. Okay.
Two particles cannot sit at the same point. Right?
Yes, I am exactly asking that. But then if I take that thing, that L minus mod x1 minus x2, then as x1 minus x2 is same, then the shortest distance will become L. The shortest x distance will also become L, and y distance will also become L. So
No. You have to understand that when you generate this random configuration of the particles, you have to take care of the fact that they are hard spheres or hard disks in 2D with a certain radius. And you can choose to scale all your lengths so that that radius becomes 1. It's your choice. So if your random number generator ever generates 2 points that are closer than the diameter of the particles, then those points have to be rejected. You cannot have, because then you are violating the model you are trying to simulate.
Then at that case, what should we choose? Short distance is mod x1 minus x2 or mod L minus x1 minus x2?
No. See, with periodic boundary conditions, it is always L minus mod x1 minus x2 along the x direction, and similarly along the y direction, right? What I'm saying is you should never get into a situation where two particles are closer to each other than their radius, because then you are violating the condition that you are simulating a system of hard spheres. So when you successively generate the positions of the particles, you have to have a check that when a new coordinate is generated for a new particle, whether it is closer to any of the existing particles than the diameter of the particles. If that happens, that point has to be rejected, and another random coordinate or a pair of random coordinates xy have to be generated.
Okay.
Is that clear?
Yes.
Okay. So what I want to talk about next is that how do you designate these lattice planes, a family of lattice planes, suppose, and as we have just found there are reciprocal lattice vectors perpendicular to any family of lattice planes. All right. So, so suppose the shortest reciprocal lattice vector perpendicular to this family of planes is HB1 plus HK, right? How do you write HK? H2. This is the family of lattice planes. Excuse me. So these planes are then designated as the HKL planes, and sort of these is called the Miller indices. So Miller indices comes from what is the shortest reciprocal lattice vector? I mean, formally that is what it is. What is the shortest lattice vector perpendicular to a family of lattice planes? Now, each one of these planes is an HKL plane. Typically, a family of lattice planes. So this is one plane. This is just a notation I'm sort of alerting you to. A family of planes would be usually designated like this, equivalent sort of planes. We'll come to this with examples to elaborate. And this direction, okay, along G. So this is designated like this. So this indicates a direction in the lines. And this notation is used for these are some notations that are sort of standard in this. So let us try to understand. So these are Miller indices, fine. But they actually, I mean, as I said, this comes from what is the shortest reciprocal lattice vector perpendicular to this family of planes. And because it's the sort of this HKL integers, because we know that integer combinations of this reciprocal primitive cell vectors, which generate these all the reciprocal lattice vectors for the reciprocal vectors for these lattice. So therefore, and since we are saying that this is the shortest reciprocal lattice vector perpendicular to this set of planes, there are no common factors between HKL. Okay, so that is something you should keep in mind. As it turns out, these numbers H, K, and L have some connection to the real space lattice also. So note that these are about the reciprocal space, okay? But they do have a connection with the real space also. So let me see if we can explain this without a figure, or it's better to.
Hello, YouTube.
Just give me a minute. I'll show you something. Yeah. Yeah, I'll just use one of these figures to sort of illustrate the point. So as you can see, you can have different sort of planes. You can have planes perpendicular to this or perpendicular, I mean, sort of parallel to this rate plane here, the rate plane here, or here, or here. There can be several types of, in the sense that directed different ways, family of lattice planes. Now, given one set of sort of family of lattice planes, let us suppose that um, uh, um, they have intersects on the direct lattice vectors, that is A1, A2, and A3, that are X1, X2, and X3. So these are
sir, we are seeing the laptop screen, not the board.
okay. Sorry. I cannot. Sorry, I cannot share both together. It's possible, but probably needs some tweaking. Okay, but okay, just see these figures, and I hope you understand what we are talking about. We are talking about a different family of lattice planes, which can have different intercepts on the real space lattice vectors. Okay, let me stop this and then go over to this. Okay, so suppose we have a certain family of lattice planes which have x1, x2, x3 intercepts on the real space lattice vectors. A3. Now, because these are lattice planes, so e to the I g dot r will have, if well g is a reciprocal lattice vector perpendicular to this, let's say it's the shortest reciprocal lattice vector perpendicular to these lattice planes, which is like this. So this will have constant values on all these lattice planes. So let us say that constant is some e, doesn't matter what it is. So so then, what is the sort of coordinate on at the point where these lattice plane intersects the A1 axis? Okay, so I said the intersect is x1, so it is x1, A1. Similarly, on the A2 axis, it is x2, A2, and on the A3 axis, it is x3, A3. So, so e to the I g dot R. So this is my R at the point where this plane intersects the A1 axis. So this will be so it's B1, so twice R is 1. Okay, so what I said was what I want to write is that not this, but let us say it's the same thing. Let us say I say G dot R is equal to on the plates. Saying the same thing. So so then what I have here is twice pi x1 stage is A, and so x stage is equal to A over x1. Or conversely, x1 is twice pi A over twice pi each. Similarly, in the other two, along the other two axes, we'll have x2 is, or let me write this as k is k over x2 and L is. So the ratio HKL is 1 over x1 is to 1 over x2, 1 over x1 is to 1 over x2 is to 1 over x3. So in other words, these Miller indices of a lattice plane are just the ratios of these Miller indices is just the ratios of the inverse of their intersects on the real space lattice vectors. In fact, that is the way sort of the experimentalists, the crystallographers often view it, but it actually comes from this sort of formal treatment that you always have a set of lattice plates perpendicular to reciprocal lattice vectors and vice versa. And you can then, given the shortest reciprocal lattice vector perpendicular to a set of planes, that uniquely defines those set of planes, and that is how they are sort of marked as the HKL, which are called the Miller indices. And turns out that the Miller indices, or the ratios of the Miller indices, are just the ratios of the inverse of the intercepts of these lattice planes on the direct space lattice vectors A1, A2, and A3. Okay, so this much was formal. Now, some convention that I should mention is that there are actually many systems which you find materials that crystallize in forms that are essentially cubic, in the sense that either FCC or BCC, or FCC or BCC with more than one atoms in the bases and so on. So therefore, cubic systems are quite common, and they have an underlying symmetry which is very simple to sort of treat and visualize. So although I showed you that the primitive lattice vectors of a BCC, for example, is so primitive lattice vectors of a BCC lattice are taken as this. And so on.
Sir?
Yes.
So majority of us can't see the board clearly. I mean, the brightness is quite low.
If you can focus a bit lower to the screen, I think it will be clear.
Okay. Does it improve anything?
Yes, sir.
Okay. Let me try to refocus it. See if it helps.
Yes, sir. Now it's clear.
Okay. And so on. So, but then it's a cubic system, right? So often while doing band structure plots, we'll probably not get into that. But doing this sort of crystallography, one talks in terms of the conventional cubic cell. So if I have to describe a BCC lattice in terms of the conventional cubic cell, the unit cell would be the lattice vector. So this is primitive cell. These are the primitive lattice vectors. The conventional cubic cell would be this is. But you remember you have one atom at each corner, but you also have another atom at the body center. So with one atom per primitive cell, I cannot describe the BCC lattice if I take these to be my lattice vectors. So then I have to have a basis which is of two atoms, one at 0, 0, 0, the other at A by 2, A by 2. So if I use this two atom basis and these set of lattice vectors, then I can describe the BCC lattice. So this is my conventional unit cell. And that is quite often used while talking about these Miller indices. So when one talks about the Miller indices of let's say FCC or BCC crystals, one typically does not mean these x1, x2, x3 to be the intercepts on these set of A1, A2, A3s. No, they are taken to mean intercepts on the conventional cubic axis. So you should keep that in mind. I mean, you have to understand that in order to interpret your experimental results, or if you are doing a calculation, you have to understand this convention to do things properly. Okay. I mean, one could define HKL or X1, X2, X3 in terms of these lattice vectors also, but that is not what is conventionally done. And when you think of a cubic system, as you can easily see, because it's a cube, so X, Y, and Z directions are all equivalent. So therefore, a 1, 0, 0 plane, okay, is the same as a 0, 1, 0 plane, and that is the same as a 0, 0. Similarly, a 1, 1, 0 plane is the same as 0, 1, 0. 0, 1 is 2 is 1, 0. These three are equivalent, these three are symmetry equivalent. So these things taken together is sort of represented as the 1, 0, 0 family of units. This would be the 1, 1, 0 family of units, and so on. Okay, so are there any questions at this point?
So would you repeat this last bit? What do you mean by they are the same plane?
They are symmetry equivalent in a cubic system.
Okay.
Okay, so if there are no other questions, what is the next thing we want to discuss? So now let us get back to, yes?
Sir?
Yes.
There would be a general rule, right, to find if two sets of Miller indices are given, whether they fall in the same family of planes or not.
See, Miller indices, as I said, are the sort of come from the shortest reciprocal lattice vector. Okay. So first of all, this H, K, and L, they do not have a common factor. So that already gives you a unique direction in the reciprocal space. I mean, in terms of the reciprocal lattice vector, and that tells you that you are talking about which sort of family of planes you are talking about. That uniquely defines it. So if you have two different sets of Miller indices, they would mean two different families of lattice planes.
Okay.
Okay, all right. So then the next thing we want to discuss is finally we go back to this discussion of scattering experiments on periodic lattices and how to sort of interpret, or what do we expect to find when we do, for example, an X-ray scattering experiment, and how does that differ from what we studied in some detail for the fluids. Okay, the first result that is very useful to understand, know and understand, is that when you have a periodic function, you take the Fourier transform. Yeah, you take the Fourier transform of a periodic function in the reciprocal space, in the Q space. You find the Fourier components only at discrete set of Q values. Is that result known to you, or I mean, are you familiar with that result or no? If Can you hear me?
Yes, we can hear you.
No, there was some problem. I got a complaint about the internet connection, so that's why.
Yes, sir. We couldn't hear you for the last 30 seconds.
Yeah, that's why. So there was a complaint that the internet connection is weak. So let me repeat. So if you have a function which is periodic in the real space and you take its Fourier transform, you get Fourier components only at a discrete set of Q values. Is this result known to you? If there's anyone who is not familiar with this, just say no, I don't know. No, I still don't understand. Are you all familiar with this result?
Is this Fourier series? What you're saying?
No, we are doing a Fourier transform. But the Fourier components that you get are non-zero only at a discrete set of reciprocal vectors, reciprocal space vectors.
Sir, discuss it, please.
Yeah, okay, I will. So remember, I mean, now on we'll only be talking about periodic solids. So we are talking about a periodic system, a system which is periodic in real space. The atoms are arranged in a periodic fashion. So there are functions of R that are periodic. For example, the atom positions are periodic functions, right? They are sort of non-zero only at certain locations. Similarly, the potentials that the electrons experience because of these ions or nuclei will also have the same periodicity. So these are periodic functions. Remember, electron wave functions or electron densities do not have the same periodicity as the lattice, and we'll understand that subsequently why. But the atom positions and the potentials that electrons experience are periodic. And suppose I have to take a Fourier transform of such a periodic function. Okay. So I have a periodic function of such that that's a periodic function. And I want its Fourier transform, which I define as now this integral is over all space, but I have a periodic function. So therefore, what I can do is I can just do this integral over one unit cell, and then sum over contributions from all unit cells. That will give me the same result because it's a periodic function. So I can write this as so what I'll do is I'll do this sum over R, then integral that will give you the same result. Now this is a periodic function, so this will give me f of R. So, minus but this integral is over the unit cell. So let me put a 0 here, which means over the unit. Now what is this? So I have some q vector, and I'm taking this e to the minus I q dot r, and I'm summing over all r's. So this will be a sum over numbers which can be both positive and negative. I mean, it's of course generally a complex number. So this sum will give me a non-zero contribution only when these things add up in a constructive way. In other words, when q is g, I'll have all these factors to be 1, all these terms to be 1, so I'll get a non-zero contribution. In other cases, for a general q, this will give me 0 because I'm summing over all r's. So therefore, and when it is g, one of the reciprocal lattice vector, what will be the contribution? Now, this is written in the following way, that it will give me NC, where NC is the number of unit cells in my physical crystal, which is considered to be large, but that is not a major consideration here. Suppose I have a piece of crystal in which I have a certain number of unit cells. So it is that number of unit cells times V naught. I'll tell you where V naught comes from, times, and this, now Q is G, so this is what I define as f of G. F of G with a delta Q, or I can write this as what is it? So yeah, I can write this as sum over G, f of G delta Qg, where f of G So that's my definition of approach. So this is the result I'm talking about. So if you have a periodic function and do its Fourier transform, you get non-zero contributions only when this Q is one of the reciprocal lattice vectors. All the other Fourier components or Fourier transforms at all other Q vectors are zero. Okay, and V naught is the volume of the unit cell. And as you can see, this is the total volume of the crystal. Okay, so this is the first sort of important piece of result that we need to use. Yeah. Then the next part is that so what I'm interested in is eventually in calculating this case of Q, the structure factor. The structure factor S of Q was 1 over V times I of Q that we had defined, which we call the structure function. So it's a normalized structure function. So this was, if you remember, we had to create an expression for this, which looked like this. I had used the index X here. So this is what we had derived in one of the earlier classes. So here what we are trying to do, what is N here? N is the average sort of density of particles. And by particles here we mean the atoms that form my crystal at the point R, and this is the Arcel function. So what we would try to do is now to evaluate this term, and we'll talk about the Arcel term later. Okay, so when you have found the Fourier transform at discrete G's, then how do you sort of do the inverse Fourier transform? Then this is defined. So that's what we want to use there. So now what we would like to do is just, yeah. So I'm only writing the first. Okay. So this by definition you see is my N of Q, average N of Q, because this is my definition of Q, the Fourier transform. So this is the first term. And N is a periodic function because my atoms are arranged periodically in my crystal. So therefore, N of Q would be non-zero only and when Q is one of the reciprocal lattice vectors. So this would be I'm using this thing here. And this I write as eventually. So V squared, 1 V cancel, and oh, sorry. It's first one with the delta function. And I can replace this delta function with a direct delta function with a factor of twice pi to the dimensions. And so V times that would be twice pi to the D. D is the spatial dimension here, times this thing, which is here. So that's the first term that will eventually I'll get because of the fact that the atoms are arranged periodically. And this S of Q will now be this thing. Is a delta function plus S of Q plus a function. Good. All right. So another piece of thing that we need is what is the sort of the scattering cross section when I do a scattering experiment on these things. So if you remember the scattering cross section when we calculated, there was one piece which came from, there was two factors actually. One that contains information about the arrangement of the atoms, which is captured by this structure factor, and the other which depended on the potential of scattering from the atoms. Okay, so that U part. So I just want you to remind you of that. So this potential U is what the scattering particles experience when they sort of scatter. I mean, it's the potential because of which the scattering particles undergo a scattering inside the material. Okay? And this has to have the same periodicity as the lattice. So when I take a Fourier transform of that potential, so then I'll again get discrete contributions only at a reciprocal lattice. So using this, if you evaluate what we call M18 prime or mod square of that, that's what we used. So the part that comes from U would eventually be, we just put U star and so on. So this is what we do. Okay, now here is the question to you, answer to your question. Saurabh, you had asked me that why are the reciprocal lattice vectors important? So one thing is that you saw that we can sort of classify and designate family of lattice planes using these reciprocal lattice vectors. But here is another place where it shows up. In scattering experiments, you have scatterings only when Q is one of the G's. So any arbitrary momentum transfer is not possible in a periodic system. You will only have scatterings in which the momentum transfer is one of the reciprocal lattice vectors. Okay, so so that is the information that you get from here. Apart from that, if you look at the form for S of Q, you find that you will basically get the structure factor to be non-zero only when Q is one of the reciprocal lattice vectors. Okay, so what do we expect in an ideal crystal? So let us try to understand. So suppose we have an ideal crystal. Ideal crystal, by ideal crystal, I mean the atoms are located at perfectly at the lattice sites. There is no deviation from that anywhere. In such a situation, and that can happen only when there are no impurities, no vacancies, and so on in a crystalline system, and it is at t equal to 0 and ignoring quantum effects. Okay, so it's an ideal system, never happens in nature. But if you have an ideal system, what is SNNQ in that case? So Manojit, what is your answer? Manojit, can you hear me?
Yes, sir.
So what is your answer? What would be SNNQ when you have an ideal crystal?
Sir, I don't know the answer.
You can try to think. So what was SNNQ? Don't look at the mathematical. You can look at the mathematical form, but you have to look at the appropriate one. So what was the sort of physical interpretation of SNNQ that we had discussed? It is some correlation function, right? So it's what correlation? Correlation between what? If there is anyone who has some idea about this, just speak up.
Correlations between fluctuations of the density.
Right. So if you understand that, then what is SNNQ in an ideal crystal?
It should be 0 because there should be no fluctuations.
Right. Absolutely. So it is 0 in an ideal crystal. So then S of Q has contribution only from the first term. And yeah. So, and in an ideal crystal, this N of G's would be the same at all G's. So you will have the same contribution at all G's and only at the G's. So, it's like delta function peaks at the reciprocal lattice vectors. But as I said, in a real crystal, that never happens because you will have, apart from other defects, you are always at a finite temperature. So there will be some thermal motion of the atoms. But even otherwise, you could have quantum fluctuations, so which would give you some diffuse nature and weight to these peaks in S of Q. There is one more sort of there is one more subtlety to this, that in this discussion we haven't brought in the complication that in real materials, it's not that you have only one atom sitting at every lattice site. As we saw, some lattices or some crystals need to be defined with more than a one atom basis. And as an example, and let me get back to that example once more, because that sort of makes that idea very clear. So I had shown you this model. So let me just bring it up once more here. So it was here, 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 here. Okay, so this. Oh, I got this. Okay. So what I had said is that so if you are sitting at this atom or if you are sitting at this atom, the arrangement around them are not the same. So this is not a Bravais. On the other hand, if I take this to be my one of my lattice vectors and this to be one of my lattice vectors, then as you can see, so one vector is this, the other vector is here. So these two atoms would fall within the unit cell. So I need two atoms to sort of describe this crystal. So you have such situations, okay? So how do you calculate A sub Q in these cases? The complication comes because of multiple atoms in your unit cell. So suppose I have atoms and locations that I mark as DJ. In each unit cell. In other words, the actual location of the atoms are at so you go to a lattice site R alpha, and from that point you take these vectors, you go along these vectors dj. Now, what values j takes depends on how many atoms you have in your basis. In the crystal that I just showed you, there are two atoms in the basis. So one of those could be, let's say, D1 is 0 and D2 is whatever that. In the picture that I showed you, D2 would be something like 1.46 or something like that for the graphene lattice along 1. So this is just one example, but you get the idea. So these are the actual physical locations of your atoms within the crystal. So then your N of X or N of R, sorry, N of R would be that's your density. Okay. And then you evaluate energy from here. And what we'll find is I made that for you to figure out. Is this. So the N of G that goes into this evaluation of S of Q would have this. So that's a structure factor. Now, when it comes to the actual, and okay, there is a name for this. So this thing is, this thing has a name, which is sometimes called the geometric structure factor or something like And then when you come to this, what is assumed here, and in the whole analysis that we did earlier, is that the potential U that the scattered particles experience is the same as all lattice points. Now, if it so happens that there are different types of atoms in your crystal, there are different types of atoms in your in each unit cell, there's no reason for you to sort of assume that the scattering potential they provide to the incoming particles would be the same. So it can vary with what type of atom is sitting where. So that is captured through a quantity called atomic form factor. It basically tells you how the potential, I mean, what is the scattering potential that is provided by each of the atoms. So I'll leave it at that level. Let us not get into further complications of that. If there is a short discussion in Ashcroft's book, you can find out. But as long as you get the physical idea, it's okay. Because we are not going to sort of trying to interpret scattering data in this course. So atomic form factor comes from the fact that different atoms can give different scattering potential to the particles. And this thing, geometric structure factor, comes in simply because you may have, in some situations, more than one atoms in your basis. Otherwise, on the right, what you have is the general analysis of the situation. And so basically, in an ideal crystal, you expect S of Q to be non-zero and like delta functions at the reciprocal lattice vectors, but thermal fluctuations, quantum fluctuations, etc., and defects, etc., would generate finite widths in these delta functions. So when you look at a sort of scattering data, you won't find absolutely sharp peaks. It never happens in reality at reciprocal lattice vectors. Okay, what else did I want to discuss here? Pretty much. So now, what about scattering conditions? Okay. So when you have scattering of, let's say, X-ray, suppose we are talking about X-ray scattering, and we are talking about elastic X-ray scattering. So then, A was the momentum with numbers of incoming particles. P prime was scattered particles. So we have this situation. Incoming, I mean, it's an elastic scattering. So Q, which is obviously K minus K. This has to be equal to one of the reciprocal lattice vectors. That's what we just figured out. So this gives me and so then if you use this, then what you get is now this is equal to that. So this is what we'll get for elastic scattering from a crystal. Okay, so suppose K is the some incoming wave, right? So K is some twice pi over lambda. So lambda is the wavelength, and G is some reciprocal lattice vector. So G would be twice pi over D or D. Yeah. I'm just saying, mod of G would be that. Where what is D here? D is the separation between lattice planes that are perpendicular to G, and N is some integer. So the shortest reciprocal lattice vector perpendicular to the family of lattice planes would be twice pi over D, and the general reciprocal lattice vector would have the magnitude twice pi over D times N. So if you plug these things in, what you will get is this is twice pi over lambda, and so twice pi over lambda, and then you plug that in, so twice pi times and there's a factor that cos theta, the angle factor will come in. So let me draw the figure here. So thing is that this is A. This is A. And this is so this would be equal to twice. So when you sort of look at the factors, so basically what you have is one is so this same result that you learned from much elementary considerations by calculating the path difference between the rays reflected from two successive lattice planes. And if their path difference happens to be an integral multiple of the wavelength, there's a constructive interference, and that's how you get this result. But from this more sort of elaborate analysis, you get the same result in the condition that it's an elastic scattering. Okay, so that completes our discussion for structure of solids, the scattering experiments, and so on. And yeah, now we'll switch gear completely, and we'll study properties of electrons, that is possible energy states of electrons when they do experience a periodic potential due to these ions. So do you have any questions at this point? Otherwise we will move on.
Sir, in our typical scattering experiment, the scattering happens through a plane, right? Plane in the Fourier space.
There are lots of words that you say. Can you sort of ask your question once again?
Okay. So in a typical scattering experiment, what I previously thought was that a single atom, or let's say at most the atom, the base is sitting at a point, lattice point is responsible for scattering. But this is slightly counterintuitive that it is happening via plane in the reciprocal lattice.
No, it's not happening in a plane in the reciprocal lattice. It is happening in the real crystal. It is happening because you have I mean, what exactly causes scattering depends on what is getting scattered. So, what is that scattering potential? U. We haven't discussed anything about the physical origins of Q. Okay. So
Okay.
that is something we cannot. I mean, I don't want to get into at this point. And yeah, so I'll leave it at that. Depends on what is getting scattered. If it is neutron, it gets scattered by something. If it's X-ray, it gets scattered by something else. All we have used is the fact that the scattering potential is periodic with the same periodicity as your real space crystal, which makes, which is should be intuitively clear, right?
Yes.
So that's all we have used. It's not getting scattered by reciprocal space planes. No, no, no. What happens is that the momentum transfer, when the scattering is happening in a periodic solid, the momentum transfer has to be equal to one of the reciprocal lattice vectors. It cannot be that Q that is written here, the momentum transfer, cannot take any arbitrary value. It has to be equal to one of the reciprocal lattice vectors. That's all we have said.
Yes. So should I think that, let's say, scattering? Okay, I am just okay. Anyway.
Yeah, why don't you think clearly and then ask me later,
No,
next class?
I just don't want to stretch it. What I was trying to say is that is it a unit cell which is responsible, or an atom in it, or something like that?
See, ultimately, things are happening at an atomic scale. Now, again, as I said, what is exactly responsible depends on what is getting scattered. Neutrons, because of the spins, may get scattered, by the nuclei even. Okay. On the other hand, X-rays are typically scattered because you have variation in electron density in the solid and so on.
Okay.
Yeah, that's a more complicated question.
Okay.
All right. Let us. Right. So we'll now start our discussion on what to expect when you have electrons moving in the periodic potential provided by the nuclei. We'll equivalently call them nuclei, ions, atoms, but you get the idea. So we still have this picture of metals in mind, although as we'll discover that this when we talk of bringing the periodic potential experienced by the electrons, we don't need to restrict ourselves to metals, but that will come towards the end of this discussion. So the set of these electrons which sort of move about, can move about in the solid, and then the nuclei or nuclei plus some core electrons are stationary at definite positions within the crystalline solid. So that's the sort of picture we have in mind. By the way, just to tell you that I have asked Chandan in the computer center that he will share these lectures, that maybe if not today, early next week. But I want to make one thing clear is that these are not these are only for your viewing, in the sense that I'm not giving these lectures in the sense of, public lecture, anyone can access. That's not the spirit of these lectures. These are lectures given as part of an MSc course in HRI. Other students in HRI are free to join in, but it's not to be generally shared, neither the class links nor the lectures, okay? Because at some level, this is informal within and for the HRI students. Okay, so with that, so let us see how to deal with electrons in a periodic potential. So now we are discarding one of the assumptions that we had started out with when studying metals. That was the free electron approximation. Electrons do not interact with anything. That approximation is now relaxed, removed. We say that electrons experience the periodic potential with of the ions. So the Hamiltonian, but the electrons themselves do not interact with each other. So we still have non-interacting electrons moving in the periodic potential of the ions. So the Hamiltonian well, this U is now so that's the periodic potential, and due to the ions, and there are no electron-electron interactions. So first we'll try to learn some basic properties of electronic wave functions, irrespective of what is the nature of this periodic potential. Doesn't matter, as long as it is periodic. So that's the only qualification about U of R at this point. And these are my electronic wave functions, and these are the Schrodinger equations. This is the Schrodinger equation that they satisfy. So what we want to show is that I have wave functions that can be, this n index will come later, it will not be immediately obvious. So let me even remove this n. So if I K, we will see where it comes from. So if we translate this electronic wave function by one of the lattice vectors, direct space lattice vectors, it transforms like this. So this clearly tells you that electronic wave functions in the periodic potential do not have the lattice periodicity. This is a very, very important condition, and this is called theorem or law of condition or whatever. So any electronic wave function in periodic potentials has to satisfy this condition. So today we'll see there are two ways that you can prove this block condition or block theorem. So today we'll try to see one of these. So let us define a translation operator T of R. So which translate any function of R by lattice vector R, which is as we've seen integer combinations of A1, A2, A3. So, okay, so this is the definition. Or it acts on or any function. That's how T of R is defined. So the first thing we want to show is that this function commutes with the Hamiltonian. And intuitively it should be clear because the Hamiltonian has the same periodicity as my lines. Okay, because this is period. So therefore it will commute with the Hamiltonian. So this is how you sort of formally do it. Now, Hamiltonian has the same periodicity as Riemannian lattice. So, R, but then this I can write as so basically what I have is TRHR acting on side is HR here acting on side. So therefore okay, that is a condition that we have found. So therefore, I can have wave functions that are simultaneous eigenfunctions of both H and TR. I can construct energy eigenfunctions that are eigenfunctions of this discrete translation operator. So the psi of R's that we have written here, these can be chosen to be simultaneous eigenfunctions of T of R, and so what are the values? So we write this as okay. So a CR is the eigenvalue of the operator T of R with psi of R as the eigenfunction. So the task now is to just find out these eigenvalues, C of R's. Oh, okay. There is one more condition that we will need, which is that, again, that is, so we'll come to this. The other thing that we need is that T of R. You can just act it on any function of R and easily show it. Okay, so as I said, the next task is to basically find these eigenvalues C of R, right? So what we do is which is but then if I, instead of this, if I acted successively with T of R prime and T of R, we would have obtained T of R. So this would be equal to, this would also be equal to C. So basically, these two would tell me that so that is an important condition that I will have got. Okay, now suppose I choose R to be one of the lattice vectors. So A1, AI, so could be any I. So I'm talking of one of these. And I can write this as I can write any number C of AI in this form with the suitable choice of xi. Xi can be real, imaginary. So any number C of AI can be in this form. So that is, let's say, for C of AI. So any R real space vector, that is vector, is an integer combination in 3D. We are writing in 3D. This. So using this and this, I can write C of R for any of this form, right? So what would that be? That would be so that was the task, right? To find the eigenvalue C of R. So this is the general form of the eigenvalue C of R. Okay, now what we do is we bring in the periodic boundary condition that we have some N1, N2, N3, some combinations of N1, N2, and N3, so that this thing is an integer, is a real integer. Okay. So that will impose some conditions on x1, x2, and x3. So in that case, so this is a real integer or conditions. So in that case, and so I write this R. So K is basically comes from these things. So we'll see this in more detail later on. Okay, so because now C has this form, you already have dots here, right? Because then if I apply this on psi of R, I'll pick up this eigenvalue. And I now know where this K comes from. K comes from these xi's. So, these will be there by some keys. This will become clearer when we go through the second proof of Locke's theorem. But as I said, this is one of the very, very important conditions that you must understand, that wave functions under periodic boundary conditions, I'm sorry, periodic potentials should satisfy this condition. All right, so I think that's what I wanted to discuss today. So do you have any questions at this point? I have sent you another assignment. Yes, Aman?
So this blocks function, this is an ansatz, right?
No. This is not an answer.
Okay, because we see the motivation, but I mean, I don't know. Proof, is it a theorem?
It's a theorem.
Oh.
It's a theorem. It's a theorem that with functions that are, energy eigenvalues, they satisfy these conditions when the potential is periodic. Any other question? Okay, if not, then